Hello and welcome to the lecture contact angle measurement. Using contact angle measurement, we are going to characterize the surface. So, here in contact angle measurement, we are having a solid. On the solid surface, we are going to place a liquid, and using the uh, use based on the characterizing how the liquid is position on the solid, we are going to characterize the surface. And so here, contact angle, it is widely used for the calculation of surface energy of solids, and it provides a good understanding of surface properties of the solid by using this simple approach. Now here, surface energy of a solid can be determined from the measurement of contact angle of pure liquid drop on the solid. So in the figure, we can see a solid and a pure liquid droplet is placed on the solid, and it is making a contact here. So, the angle, this angle is nothing but contact angle, and the angle that we are getting here determines the surface properties. And contact angle measurement, this can be used to study surface energy, wettability, and adhesion of low surface energy materials. So wettability is how easily the surface will become wet, and adhesion is about how the surface will allow uh, a layer to stick on the surface. Suppose if we place another layer on the surface, how easily it can stick to the surface. So that is adhesion, and we can study all these things using contact angle measurement. Now here, suppose when we find the water contact angle, in that case, we are going to place a water droplet on the surface and find the water contact angle, and that can determine whether the surface is hydrophobic or hydrophilic. In case the surface is hydrophobic, it will repel the water. So whereas a hydrophilic surface is nothing but something which sticks the water, where water can easily uh, the hydrophilic surface is the surface which absorbs water easily, and so contact angle can detect differences in the substrates. So when we have multiple substrates, we can find the differences in the substrates by performing the contact angle measurement and studying the surface properties. So contact angle is the angle formed by intersection of liquid solid interface and the liquid wafer interface. So here we have liquid solid interface. This is the liquid solid interface, and this is liquid vapor interface. This is liquid and this is vapor, which can be said as gas as well. So liquid vapor interface is this one, and liquid solid interface is this, and the angle between that is contact angle. Now, so contact angle measurement by drop shape analysis. That is, here in this, we are going to analyze the shape of the drop. Now, for the drop shape analysis, there are two assumptions made. First, that is drop is symmetrical about a central vertical axis. So, at the center of the droplet, a vertical axis is is assumed, and about that axis, the drop is symmetrical. That is, it appears in the same it appears similar whatever the direction, at whatever the side you see from the vertical axis. Now the drop is not in motion. That is, viscosity and inertia are playing key role in determining the shape. So here, viscosity and inertia, that is going to determine the shape, and so interfacial tension and gravity are the only two forces that are shaping the drop. So the shape of the drop is due to interfacial tension and gravity. Now, so here the drop is not in motion, which means viscosity and inertia are playing key role in determining the shape. Now, a drop of incompressible liquid on a surface is held in equilibrium by balance of two forces. There are short range attractive forces. So because of this, the drop will be intact in shape on the surface. And there is another force, electrostatic repulsive forces. So these forces will try to distort the shape of the drop of liquid. Now there will be another force, which is surface tension force, which keeps the drop in uh, virginal position. So surface tension uh, is always trying to keep the drop in virginal position. Now, if electrostatic repulsive forces become greater than attractive forces, so what will happen? The shape of the drop gets distorted. First it will become dumbbell shape. Now, what will happen? The surface tension always tries to keep the drop in its shape. So as the drop becomes dumbbell shape uh, because of electrostatic repulsive forces greater than attractive, then it will becomes dumbbell. Then surface tension will act, and it will split the drop to become two drops. As you can see here, it will become two drops. Now here in this figure, you can see that three drops are there in three different shapes. So here we can understand how what is the contact angle for these three drops. So when theta is less than 90, you can see the shape of the drop, and for theta is equal to 90, it's like exactly a half circle is present on the like half sphere exactly. If you cut uh, a sphere into two parts, and if you place on the surface, then that is the shape of the uh, liquid droplet. For theta is equal to 90, and for theta greater than 90, it is more than that. So you can see found by liquid sessile drops on a smooth homogeneous solid surface. So homogeneous, always we are going to do on a homogeneous solid surface. So here it homogeneous means the surface is similar throughout. Like homogeneous means surface is similar throughout the area of interest. So based on that, we are going to determine if the surface is not homogeneous, then we cannot uh, study the surface properties with the contact angle measurement. So surface must be smooth and it must be homogeneous. If contact angle is low, then wetting capability will be high. That is, uh, the surface can be wetted more. That is, wetting capability is high. That is, the liquid can easily spread on the substrate. So here wetting capability means if wetting capability is high, the liquid can easily spread on the substrate. That happens for theta greater than 90. And for contact angle theta greater than 90, the wetting capability will be low. And for theta is equal to 90, it is moderate. So it's a degree of wettability. Contact angle here determines the degree of wettability. Now here in this figure, we can see the three forces which are acting on the liquid, and we can see the contact angle theta. So solid liquid wafer, and so three forces are given as here we are represented with gamma. Now each force is pulling away from the equilibrium point. So if the droplet is in equilibrium, the forces are balanced. Now from the Young's equation, the contact angle of a liquid drop on an ideal surface is defined by the mechanical equilibrium of drop under the action of three interfacial tensions. So here gamma LV is the interfacial tension between liquid and vapor, And gamma SV is between solid, interfacial tension between solid and vapor, and other one is between solid and liquid. So, then to calculate, so here all three interfacial tensions are related to contact angle. Now here cos theta is equal to gamma SV minus gamma SL by gamma LV. Now based on the amount of tensions, we can determine theta. Suppose if gamma SV is less than gamma SL, in that case cos theta will be negative, as you can see in this equation. If this is lesser than this, cos theta will be negative and theta is greater than 90. And this occurs with high surface energy solid or low surface tension liquid. And uh, for gamma SV greater than gamma SL, cos theta is positive and theta is less than 90. This occurs with a low surface energy liquid or a high surface. This is low surface energy solid or high surface tension liquid. Please make a correction that this is solid, low surface energy solid. So for theta greater than 90, wettability will be high. So when wettability will be high, the wettability will be high for a low surface energy solid. Here, please replace it with solid. And so this is an experimental setup for contact angle measurement, where we have a illuminator, liquid lens, telescope, high-speed camera, and this is connected to a software system. And these are all given power from a power amplifier function generator. Also to operate everything, and we have illuminator. Illuminator has light source, and here drop is eliminated and image is recorded by camera. So illuminator will eliminate the drop which is placed in this lens, and the image is recorded by high speed camera. Now the image is analyzed by using the software system, and then we will determine contact angle. Now here this setup, it has optical components, so this might increase the cost, but overall the system is simple to study the surface properties of the substrate. Now here important aspects of the image for the purpose of contact angle measurement. So when we get the image, so to determine the contact angle measurement accurately, there are certain important aspects here, like image size. Now the image must contain the entire droplet, so then only we can measure, then only we can see its edge and measure the angle correctly. Otherwise you cannot measure the contact angle if you can't see the edges of the droplet. Now clarity is that you need to be able to see the droplet clearly. uh, the better the clarity of the edges, the more accurately you will be able to measure the contact angle. Now, a fuzzy droplet edge will make it harder to see both the slope of the droplet and the place at which it meets the solid surface. Like if a fuzzy droplet, if the droplet edge is not clear and it's fuzzy, then it will be harder to see the slope of the droplet, and where it meets the solid surface. So we cannot get the clear picture of contact angle. Now this clarity can be affected by factors such as camera resolution, image magnification, light levels, and contrast with the background. So camera resolution, it determines how many pixels represent the droplet edge. Now, if the image is highly pixelated, if the image has high number of pixels, then it is hard to determine where the edge of the droplet is. So it is difficult to determine exact edge of the droplet. Now, for polynomial fitting, the fewer the data points, the less accurate the fit. So the number of data points should be more for polynomial fitting. And magnification. Image magnification has an impact on resolution. So the larger an optical image is, the more pixels it will cover, and the high resolution the image will be. So this is the importance of magnification. And contrast, it is important for finding the droplet edge. When there is no contrast, if the contrast is less, then we cannot sharply uh, pick the edge of the droplet. So in that sense, contrast will play a vital role or very important role in finding the droplet edge very sharply, and so that will means for calculating contact angle accurately. Now, when if there is low contrast, then it will hard to separate the droplet from its background. So there must, it will be overlapping like the background as well as droplet. And if you are using an edge detection technique, contrast will determine the detection accuracy. So in edge detection technique, contrast will determine detection accuracy. And lighting as well here. Lighting levels can also affect the measurement. And so because we must be able to see the droplet to take a measurement. So when the lighting level is good, we can see the drop, that is camera can see the droplet uh, clearly and it can record properly. And if the lighting is too light, means if there is more light or too dark, the contrast of the droplet and background also can be affected. Now here depth of the field. So what here depth of the field will do, like if you want the entire depth of the droplet to be in focus, otherwise it will be difficult to find the baseline through the blurry front of the droplet. So this can be achieved by altering the depth of the field of the imaging system. So now here the actual focal point of a lens is a specific distance from it. However, there is an either area side of the focal point which you consider to be in focus. So this is known as a depth of field. The depth of field, this can be altered by using an aperture. Now here the image below shows the effect of an aperture on the light entering camera. So as the aperture is reduced in, so the figure is here as shown in this on the light entry. So it will shows the effect of an aperture on the light entering a camera. So as the aperture is reduced in size, the light entering the camera is narrowed. So here you can see the, so what does the depth of the field? So from these two cases, you can see the depth of field in the above one is narrow and it is wider here. Now, as the aperture is reduced in size, the light entering the camera is narrowed. So when the aperture size is narrowed, the light entering the camera is narrowed here. So in the second case, it is very narrow, the light entering the camera. Now this results in two changes. There is less overall light, so you need a bright background light, or the depth of field is increased and the in focus region becomes longer. So now here, as the aperture is narrowed, the size of the beam changes. If you consider the focal region to be within a certain beam width, you can extend this focal region away from the camera by narrowing the ring. So the result of this is shown in below figure here. In the first image, the depth of the field starts and ends inside the droplet itself. So here, this is the droplet, and the depth of the field starts and ends in the droplet itself. So the front and back of the droplet are blurry. That is, the droplet here and here it will become blurry. Now in the second image, the in the second image, the depth of the field is wider then the whole droplet, that is here, this is the depth of the droplet and this is droplet. So the entire droplet is within the focus. So by this, when we are increasing the depth of the field, we are able to detect the edge properly. So because we are not going to get blurriness in the second case. So this is how we are uh, going to calculate contact angle and determine surface properties. And so this is the end of the lecture. Thank you for watching, and if you're watching for the first time, please subscribe my channel and